Hello guys, so yeah, welcome to our last workshop for ROS workshop in deep learning in robotics for this semester. So this would be the final workshop in this semester, and this would be quite an advanced one as we're going to use YOLO and deploy it on ROS. So before that, I'm going to introduce myself. I'm Nelson. I'm currently at Triple E year 4, and I'm in MLDA at Triple E. So MLDA at Triple E is MLDA at Triple E provide a platform for Triple E students, NTU students, to learn and implement about data science, artificial intelligence, as well as machine learning. And we'll do that by providing workshops such as this one. And we also have resources such as GPU that we have in the lab. We also host some events such as Deep Learning Week that happens 2 weeks ago. So for this workshop, we're currently conducting this by MLDA Robotics. So MLDA Robotics is a new initiative from MLDA Triple E. And the idea is that we want to integrate deep learning into robotics. And what kind of activities we have here is that we have workshops such as this one. We also have some projects that we've conducted previously, such as Telodrone project, and we have many more to do. And the main objective is to do a competition, and the competition that we're currently going to compete in is the RoboMaster competition. Aside from that, our workshop currently is actually conducted collaborated with UAVIONICS Club. So I think Junse can do a brief presentation about that.
Okay, thanks, Nelson. So hello, everyone. Welcome to this workshop. So I'm Chinza from UAVIONICS. Basically, the aim of UAVIONICS Club is actually to build UAVs, which stands for Unmanned Autonomous Vehicles, either in the area of air, such that we have the micro drones, or in the area of land, like we have the autonomous Raspberry Pi car or autonomous Jetson Nano car. So if you all think that this is something you might be interested in, do feel free to join us. And we are still actively recruiting for new members. And yeah, we'll be having more workshops and activities in the coming semester. And yeah, do feel free to hit us up. So that's all from my side.
Okay, thank you, Junse. So continuing on. So for this workshop, our main flow would be to train our YOLO object detection. That is to collect data in gazebo simulation that we have previously used in the previous workshop. We're also going to do a data annotation, and then train and test the YOLO V5 model. And finally, the hands-on session for this workshop would be to deploy a YOLO V5 model in gazebo itself to do one of the application of this YOLO V5 is to do a robot pursuit. So I'm going to show you how you can do it in this workshop. So for this workshop itself, it's going to be more complicated compared to the previous one because we're not allowed to use this. This is because we might do heavy computation using object detection model that we're going to deploy itself. So we can run it on the construct sim. So for this workshop, you guys have to have like ROS deployed on Docker container, or you can also have like local machine running ROS. So those two are okay, but this one we can't do it for this workshop. So before we start the workshop itself, I think I am going to show you guys what you guys will be doing and expect to do for this workshop. So I'm going to launch the RVs and the gazebo simulation. So as you guys can see, this is the gazebo simulation over here, and there are two robots. So let me zoom here. So this robot will be the pursuer, and this robot, which is the one that we can control to our teleop controller. Let me show you. Yeah, so as you can see, I'm controlling this robot right here. So this robot is going to be chased by this robot or going to be pursued by this robot. So as you guys can see, there are a lot of obstacles around the way, and these obstacles can be identified by not to be identified, but this robot can be distinguished from these obstacles by our object detection model. So if you guys see here, this is what the robot is seeing, but actually you guys can also see that there's an inference topic that can be seen from here. So as you guys can see, this is what the robot will be doing. So it will be detecting the location of the robot itself with regards to its position towards the center of the camera. So yeah, if you guys see here, yeah, the robot is still pursuing. And if I, let's say, change my direction or something like this, the robot should be able to find where I'm going right now, and it's going to pursue it. Yeah. So yeah, that's what we're going to do in this workshop. So hopefully you guys are excited. And for this workshop itself, you guys have to at least have some knowledge about PID controller that has been discussed in the previous workshop, and how to create your own publisher and subscriber. Yep. So first of all, as you guys can see, the object detection model is basically taking the input of an image data, and then it detects where the object is and create a bounding box. So before that, we have to understand what is image itself and how it is being represented in our computer, or in our, if we're using Python or C++, how is it going to be represented itself? So first of all, image can be represented in a matrix pixels, in a three-dimensional matrix, you can see. So you can see there's the width, there's the height, and there's the channel. So the channel is like the depth. So as you guys can see just now, it was an RGB image, and there are another type of, I guess you can say there's another type of channel, several channels in the image. The other one is the grayscale image that you guys have seen, probably have seen before. So for this scenario, we'll be using RGB or BGR channel, which consists of red, green, and blue channel. That is the most common one for image. And what is object detection? So object detection, as you guys have seen from the demo itself, is to detect the location of the object and draw a bounding box. So this bounding box consists of 6 different parameters. So the first one is the X coordinate of this, I guess this corner, and then the Y coordinate is the second one. And then for this one as well, so X, Y for this one. So there will be 4 coordinates, 2 coordinates consists of X, Y. And then the last 2 parameters would be the label and the accuracy itself. So, or the confidence, you can say. So the confidence here. So it's not clearly shown here, but you guys can later see when you guys actually deploy it on your laptop, and you guys can zoom for the image. Yeah. So for this object detection, we have to collect our data in Gazebo. So I'm going to show you guys how are we going to collect data in Gazebo later on. So after we collect our data in Gazebo, we need to annotate them, and we're going to use this label IMG right here. Yeah. So this is clearly open source, and we can just install and set it up in like 1 minute or so. So I'm going to show you guys that. And if you guys haven't started pulling your Docker image, I suggest you guys to pull it right now. So we have 2 different versions. The first one is the CPU version. So that means you'll be running the inference on CPU. And the second one is the CUDA version. For the CUDA version, you will need to have graphics card, NVIDIA graphics card supported on your computer. And you can check it out by writing NVIDIA SMI. And as you can see, there's clearly a GPU running on my computer, so that should be fine for me. But if you guys don't have this running, then it's better to use the CPU version. And another thing that you need to consider is that since we're running it on Zoom right now, like we're running Zoom as well as this together, you might need to have at least 4 gigabytes of GPU memory to ensure that you can run everything smoothly. So if you only have like, let's say 2 gigabytes of memory, then I suggest you guys to pull this one. And the command is quite simple. You guys just need to use this command, docker pull, and then specify the tag. So I think I put it around here. Yeah. So docker pull, and then just specify either you want to use the CPU or the CUDA version. And this might take a bit longer, so I suggest you guys to do this right now, unless you guys already have your ROS running on your laptop or on your computer, then you guys don't have to do this. But we're running it on Ubuntu 20 with ROS Kinetic. So if you're using different types of ROS, then I suggest you guys to do this as well. And it's not difficult to install Docker itself because I think I've set it up here for Ubuntu. For the Windows, I think you guys just need to follow the Docker installation from the website. Yeah. Lastly, after doing the, oh yeah, I'm going to share this first. Okay. Let me share it first. Yeah. So you guys can pull the Docker container. The label IMG, I'm going to share that data. So lastly, this should be the expected result when we train our YOLO model. So as you guys can see over here, there's the confidence, there's the label itself, which is robot, and you can see the bounding box. So the bounding box must be created by two different coordinates, XY and XY over here, the top left and the bottom right. And for those who understand object detection, as in machine learning model in general, then this is the expected epoch loss. So if we're going to train our model, as I've trained it before, the model will be converging after around 300 epoch, as you can see from the validation loss with respect to the train loss. So yeah, around 300 epoch, our model should be converging, and we should have an expected result of something like this. So I'm going to show you guys how to do this itself. So for this workshop, the code is already inside this GitHub right here. So I'm going to share it to you guys as well. Share this. Yeah. So thing will take around 1 minute for you guys to clone. Okay, I think I'm just going to show it here. So for those who use Ubuntu, you guys can just create, for everybody actually, just create a new directory and name this something. Let's say YOLO workspace. Yep. So new folder, create SRC. And for this SRC, we're going to clone this. So git clone. Okay. Okay, so you guys should have something like this after cloning it. And in addition to that, I think because I'm running in Ubuntu 18 and I'm using ROS Melodic, so I need to pull the Docker container, which I've done. So to pull the Docker container, just need to do docker pull Nelson UW workshop 3 and CUDA. Yeah, so for me it is up to date, but for you guys, I think there will be some comment over here and it will start pulling it. Yeah, it may take a bit of time, so you guys need to do it fast. And then once we are done with it, we should do this. So copy this, create a run container.bash. So I'm going to create it over here. Create it. Run container.bash. Paste it over here. And then below, we need to specify that we want to use CUDA. For me, I'm going to use CUDA. And inside here, my path to my Catkin workspace with respect to home is home, the username, YOLO workspace. Yeah. So YOLO workspace is after my home, username, YOLO workspace. So I'm just going to put it here. Save it. close. As you can see, it's not executable yet. So if I do // I'm not going to get anything if I press tab. So I need to change it to executable. So now if I do this, yeah, you can see the auto completion works. And don't worry if you guys have this Catkin workspace no such file directory. It's because we haven't built itself or make, yeah. So first things first, we're going to go to the Catkin workspace. So this Catkin workspace is actually the same as YOLO workspace. It's going to be remapped by Docker. So let's say I create something like let's say a new directory, for example, test. If I type ls here, this will be represented here. So that's how Docker works. Yeah, I'm going to delete this. So first things first, we're going to catkin make. Yeah. While we're waiting for this catkin make to do its stuff, here I'm going to open. So I'm assuming you guys will be using VS Code in your computer. So first things first, we open a new window from our VS Code. Then we need to install a specific extension in VS Code called remote containers. So install this and press this one, then press connect to host. Sorry, not this one. Attached to running container. So there are two over here because I'm actually running the other one here. So let me kill this one first. But for you guys, there should be only one. So let me try it again. Attach to running container. Yeah, there should be only one for you guys. Yeah, then press that. So I can just close this one. Okay. So I've set it up in such a way that it should open the SRC directory. But if you guys don't have that, then you should press open directory over here. There should be a pop-up around here, and then type Catkin workspace SRC, and you should have something like this. Okay, so I think the Catkin make should be finished by now. Yep. So to continue, first things first, I'm going to explain about what are all of these briefly. So let me see if I can zoom it. Okay. Yeah. So first things first, the most important part for this workshop is the Tobot tree controller and detection. The rest, I think, has been explained or touched by the previous workshop. So the main thing here is that Tobot tree detection, there are two different nodes, which are inference and node to JPEG. So I'm going to explain a bit of how are we going to collect data from Gazebo. So the idea of collecting data from Gazebo is that we already have a camera running on the robot itself from the previous workshop. So we already know the topic, and the topic is called Turtlebot1 camera RGB image raw. So this can be from, let's say, from your own robot, you already have a camera running, and you can just subscribe to that specific topic. After subscribing to that topic, we convert it from ROS message into OpenCV message, which is NumPy array. And then every time I press space, I want to save that in the directory where I'm running it. So I'm going to show you guys how we can run this. And then we're going to run everything together. So we need a launch file, and the launch file is located inside the Turtlebot tree bring up pursuit.launch. Yeah. So for this one, I'm going to comment this thing out as we're going to use this later. So these two will be the detection, which is the inference, and the controller that we're going to run later on. But for now, we're going to collect the data first. So I'm going to uncomment this too. So teleoptics keyboard, and the input topic should be camera RGB image raw. Okay. Save. And now we can source our default .dash. Then we can launch our TurtleBot 3 pursue. Bring up first. Bring up. TurtleBot 3 pursue. And there should be an error. So we need to tell that we're going to use waffle. And then we can launch it. So there are two teleop twist keyboard. And I'm running it on my Catkin workspace directory. So if I press space over here, the counter goes to 1. And this counter actually will be saved inside. Where is it? Let me change the directory first. So as I mentioned earlier, the image will be saved in the directory, and I think we need to create a directory that is linked to our YOLO workspace so that we can collect data easier. So maybe we go to our SRC, and then we can just create robot dataset. So we go inside the robot dataset now. So inside the robot dataset, we want to collect as many data as we want. So to do that, we can just run it again. Hold on. What to not to JPEG. Yeah, by right it should be safe over there. So let me see what's the problem. Okay. For now, I'm going to just hard code it. Pin workspace source robot dataset. Okay. Robot dataset. Okay. Save it. Pin workspace source robot dataset. Robot. Yeah. Okay. Okay. Now if I press space, it should be saved inside the robot dataset. Yeah. Yeah, so there's a minor bug over there, but for now we can just solve it by typing the full path. So later, if you create the directory, just create the full path from your Catkin workspace or your YOLO workspace. But this should be inside your Docker container. So the full path should be from your root, Catkin workspace source, robot dataset, and then whatever you want. And every time I press space over here, the counter goes up. So if I press space, you can see here it's 1. If I press space, it goes to 2, 3, and so on and so forth. And this will be reflected over here. So by right, what you guys need to do is that there are 2 different controllers over here. Yeah. So if I move this one, this will actually control the robot to move forward and backward. Yeah, so I'm currently controlling the robot to move forward, backward, and left, right, as you can see. And this one should control the other robot. Oops. So this one should control the other robot. So if you guys see, I'm controlling the other robot now. Yeah. So the way we collect data set is by controlling these 2. Then once we get a perfect frame that we want to take as a data, we go to this window and then press space. And this should be reflected over here. Yeah. So yeah, you guys should do this as many times as you guys want. But for this workshop, we don't have enough time to do this manually, so I've done this prior to this workshop. So let me kill this terminal first. So let's say you guys have the data, like let's say for this case, we only have 5. What we need to do is now we need to label this one by one. So how are we going to do this? So just need to open our terminal in the directory that the image was saved. So that's the directory. And then we need to install label img. So the command should be pip install label img. So I've done that in my computer, and then I just need to run it here. Yep. Then we just need to press the open directory. Then we just press open. Then you guys can see that I'm currently labeling it. So let's say this is the robot that we want to detect. Just need to create the bounding box over here, and then make sure that we save it as YOLO because we're going to use a YOLO model. Yep. And then you guys can adjust it after that. So once you guys are okay with the bounding box, you can press save and then put it on the same place for now. And then carry on. Yep. Save them. Yes. Okay. Next. Oh yeah. So yeah, now this is the new one. We can do the same thing again and again. So yep, robot. And make sure that the label is the same for all. Yeah, save it. Okay, next. Okay. What's the problem here? Next image. Yeah, so you guys need to do this over and over again. So in this case, the reason why it's not being saved is because the directory is currently held by someone else, which is the root. So when you want to save it, I guess you guys can change the directory first and put it somewhere else first over here. But the other way around is to just change the owner to yourself. So your user and then the directory. Yeah, okay. And then now this should be good to go. So do it again, robot. Yes. Okay, now it's working. So yeah, you can see this is something that should be expected. So you guys need to do this one by one. So for every image. So once you guys have done this, we can go to the YOLO v5 repository. So this is the YOLO v5 repository. So we don't have to clone it on our laptop necessarily. We're going to clone it on our GPU, where we're going to train the container. Sorry, the model, not the container. The model, yeah. So over here, you guys can see there are a lot of things that can be done. There are a lot of tutorials. So we're going to do the train custom data. So this is the train custom data. So first of all, we need to prepare our data set. And we have done this. So this should be saved inside the name itself. So 0.4. So this one tells you the first object and the label is called robot.txt robot. So it's saved in the class txt. So this is the label 0. Since we only have one object, that should be only 0. And the rest here is the x and y, x and y. X, y, x, y. So yeah. So what we need to do over here is that we need to create a dataset YAML. This dataset YAML tells you where is the location of the dataset with respect to this YOLO v5 repository when we git clone it later. And then we should tell there's a train validation directory inside this specific datasets. And the number of class for our case should be 1, and the name should be robot, and the rest should be empty here. So we don't need to do the rest here, just change this to robot. So I'm going to do that later. And lastly, we need to organize the directory in such a way that we have the image and labels directory. So for this scenario, what we need to do is that we need to create the directory called image later. Maybe before that, we need to create the directory called train and test or validation, train and validation. And then inside the train and validation, there should be images and labels. Yep. So maybe let's say we want to use these 3 images as our train. So we put it inside the train and put it inside the image. And there should be the label, the label as well. So for this case, the label should be located over here as well. And then for the validation, maybe we want to take this 3 and 4. So we do that, and then we create images and labels as well. And then we put it inside the image and labels. So yeah, for this one, we haven't do that. Yeah, so basically that's how it's going to be. We're going to put the label. So for this one is the 2. So I'm just going to put it on the labels. Yeah, so by right, there should be 3 labels. For this case, 3 image. That means there should be corresponding label with the same name, but with .txt. And similarly, in the validation, there should be the same thing over here. So there should be 2 image and 2 labels inside here. So by right, you guys need to do this one by one. So for this workshop, I've done it for you guys. As you can see, the template is basically we need to have train and validation directory and images and labels inside those. So I've done it inside the MLDA Robotics workshop that you guys clone it just now. There should be robot data set. And you can see there's the train and validation. So this robot dataset YAML, as I mentioned, I'm going to explain how we're going to create this. And then this train and val, as you can see, there's image and labels. So yeah. So these are the validation image with the corresponding and the corresponding labels as well. Similarly, in the train, we also have those and labels. Yep. So this directory is the one that we're going to pass into our GPU. So luckily, I have my GPU running over here. So we have finished the first 2 steps, which are data collection and data annotation. And the next thing is that we're going to actually run it. So to run this, first things first, we need, so let me clear this one. Yeah. So, okay. So first things first, as you can see here, I already cloned the YOLO V5. If you have, so this is inside my GPU, by the way. So this is currently running in the GPU. So this is not in my laptop. As you can see, it has 4 GPU that we can use. Currently, we can use 3 of them. So what we need to do now is that we need to clone YOLO V5. So I've done it here. As you can see, there's YOLO V5. And if you guys haven't done so, you just need to follow the command. I think you just need to do git clone. I think it's located over here. So just copy this. Pip install -r is later on. We are going to do that later on. So first things first, git clone. Yeah. So git clone this. I don't think that will work because YOLO V5 already exists. So for you guys, there should be like, okay, it's going to download or cloning this directory, this repository. So since we have done this, it's not going to allow it for us. Then the second thing we need to do is that we need to install this requirements.txt. So what we need to do is that we need to create a new environment. So conda create, let me see the command. So new environment, you can just see in here, conda create new environment. So yeah, I'm going to use Anaconda. And what we can do is, I think we can just, let me see where to create -n, create new environment. with Python version. Yeah. Okay. So we just need to specify the name and the version itself. So over here, we're going to create, the name is YOLO Workshop. And then the Python version that we're going to use is Python 3.8.10. So Python equals to 3.8.10. Let's see whether it works. Yep. Proceed. Yes. So it's going to create a new environment called Conda Activate Workshop or something like that. So I'm just going to do that. Okay, so we're in here. So if I do Python, it should see that we should see that this is the same version as the one that we're going to run on the ROS 3.8.10. Same. So everything is good. Now what we need to do is that we need to install the requirements. So we go to YOLO v5 as mentioned, pip3 install -r requirements.txt. Yeah. So we're just going to run this, but bear in mind that we're going to install PyTorch again, even though it's been installed over here, as you can see, 1.10 CP. That means we're going to use the CPU, and we're not going to use the CPU to train this. So what we need to do is that we need to go to Torch. Okay, just search Torch. Okay, get started PyTorch. Okay. So press the get started button. And as you can see here, there should be a stable version. And since we're running it on GPU, your GPU should be running on Linux usually. Or if you're using Google Colab, it should also be Linux. So you can choose Conda or Python. For now, I'm going to use Conda because I'm in the GPU, I have Conda running here. So we're going to use Conda. And then Python, then CUDA 11.3. So if you see over here, I think I cleared it, but this is actually running on CUDA version 11. So regardless of 11.1 or 2 or 3 or 4, you guys just use the same CUDA. It should run properly. And then just copy this. So I've copied this. So once it finished installing, so it's going to finish installing soon. Yeah. Yep. Okay. Okay. It might take a bit while, so we can just wait for it. Okay. Okay, it's done. So next thing is that we need to install again PyTorch, but this time we're using the GPU version. So let's specify here the CUDA toolkit. Proceed, yes. Press enter. So yeah, it's with Conda we are allowed to do pip and Conda installation. For those who don't know yet, yeah, you can use Conda install, pip install inside the Conda environment. Just make sure that you are inside the Conda environment first and activate it. Yeah. So this is going to install. Yeah, might take a bit while here. Yeah. So yeah, let me open new terminal. So let's say we have done so. We can. So this is another environment that I've set it up. So in case the internet is quite slow like this, like it takes a bit of while to install this. So I'm going to just fast forward and use another environment that I've created for this workshop. So after running those two commands, we basically have set up the requirements and the dependencies for this specific for running the YOLO v5 model. So now we can get back to the robot dataset.yaml. So I think that's the first step in this, but we can do it the other way around. So inside here, I'm going to actually split the screen so you guys can clearly see it. So inside here, we need to tell where is our robot dataset with respect to our GPU. So if you see here, how am I going to get this robot dataset from my laptop? Well, that's easy. You just need to drag this. So this is your dataset, basically, the one that I just mentioned. Drag this, put it here. So I'm not going to do that, but you guys can just do it here. So if you do that, the robot dataset will be uploaded to the GPU. I've done it here. So yeah, you guys need to do that. If you guys have custom dataset, then you have to do that as well. Yeah, so we have the train image, train labels, file image, file labels. The class txt is not required, but yeah, let's say we have target robot or something. That's not really important. So once we have the robot dataset in the root directory in the same level as YOLO v5, then what we need to do is that we create the robot dataset now. So let me hide this terminal first. So this robot dataset that is mentioned, we need to tell the path from our YOLO v5 to the dataset. For this case, it's the same level, so we need to tell the script later on that we need to move to the parent directory and then go to the robot dataset directory. And inside the robot dataset directory, there's a train directory and file directory. So that's simple as writing this train and validation as it is. We can just full screen. Yeah. Then the test is not is optional, so we don't need to write it. And then the number of class should be only one, and the name is robot. So you guys can change this to whatever you guys want. For this case, I'm just going to name it robot. You can name it target robot or etc. etc. But it should be the same for all. So yeah. So yeah, I think we're just going to skip that one. Yeah, by right, this should be fast, but maybe because I'm running it with, I'm not sure why, but yeah, we already have another environment here, so that should be fine. So this environment already set up the dependency of the YOLO that is stated here. So we have done this step, we have done this step, and we also have organized in such a way that it will work. And here there are 4 different models that are supported over here, and we should see that when we're running robotics application that requires real time, we might prefer the small one. So over here, there's the small one. So what we need to do is that we just need to train it like this. So what we need to specify is that what are the script that we need, the image size, and then the batch size itself, the number of epoch, and then where is the dataset.yaml file that we just specified. So that should be inside the same directory as yolo.v5, YOLO v5 directory. So we don't need to specify other stuff. So this is the relative path, and then the YOLO v5 spt is the one that we want to use. So we'll specify it with YOLO v5. So this is the script that we want to run. So if you have only one GPU, then it's better to run this script. And since I have like 3 GPU that can be run, for those who have more than one GPU, you can actually use this command as well. So python-m torch distributed launch number of per node. Yeah, just copy the entire thing here. So yeah. So let me go to your YOLO v5 directory. So as you can see, the robot dataset is in the directory of YOLO v5, and we tell it that the dataset is in the parent directory of this YOLO v5, which is in the home directory. So everything should work like this. Then we just need to paste it, and then modify some of it. So let me go. Okay. So for PyTorch version 1.10 and above, you guys can actually change the dot launch to run. I think it's mentioned over here. With 1.9 above, you can use the run instead of the launch. So just remove the launch, change it to run. So over here, I'm just going to delete the launch, change the run. Number of node that we're going to use is basically, if we have batch 64, means that we have to have a multiple of the number of nodes. So in this case, if we're using batch size of 64, then our node must be either 1, 2, 4, or 8, or so on and so forth, which is the number of GPU. So since currently I can only run like 3 GPU, so this one should be 2. And then the batch is 64, and you guys can just leave it as it is. If you guys have more data, then you can increase it. Since our data size is quite small, which is like 35 image for the train and 15 for the test, we're just going to leave it as it is. And then replace this Coco by whatever your name is over here. So robot data set for our case. But yeah, if you guys create your own YAML file, just replace it with whatever you guys like. Then the weights, we're going to use the small one. Then device is 3, 2, and 3. Yeah, we're going to use the last two. Yep. Yeah. So yeah, this is currently running. So it's going to scan the entire image and see whether everything is okay. Yeah, and now it's running. So currently it's training right now, as you can see. This is training 1 epoch, 2 epoch, 3 epoch, and so on and so forth. Yeah. Yeah, so for now, yeah, actually it's done. We can actually use this YOLO workspace as well if you want, but it's going to be the same environment. So yeah, so currently it's training. So if you guys have any questions, you guys can just put it in the chat first while we're waiting for this to train. Let me see if there's any questions that can help. Okay, no questions so far. Okay. Yeah, so let me review the step again. So first things first, we collect the data set. And to collect the data set, we need to run this node to JPEG script Python. And then we tell where the directory is, increment every time we want to have a new image, and save it somewhere that you guys want. After that, once we already save it in, let's say, robot dataset over here, we need to create the we need to label them or annotate them. So W direct. So that's the shortcut. You can use W, or you can just press this create red box, put it there, save it, and then go to the next image and so on and so forth. Okay, so I'm not going to do that. Yeah, let me close this. Okay. Yeah. So once you guys have that, make sure that the directory is the structure of the directory should be something like this. So your dataset directory, train directory, and validation directory, and then image labels and labels directory for both. And then just put the labels inside and put the image inside. Yeah. So that's how you guys can do that. And after that, if we go to the GPU, we need to git clone this YOLO v5, set up the environment. So pip install -r requirements.txt. And then make sure that since this PyTorch is going to use the CPU, we need to install it with the GPU version. So over here, this is the GPU version. And then once that's settled, you guys just need to run the script. So yeah, so the training is going to be done right now. Okay, so yeah, so the train, so we have trained our model successfully, YOLO v5s, and then it says that the results are going to be saved in runs trains experiment 9. So I've done a lot of training before. So for those who have just done it like the first time, there should be only exp directory, but I've done it like 8 times for other stuff. So inside the exp9 directory, or for your case should be the exp directory, there should be weights, best PT and last PT that we're going to use later on, as well as this entire thing. So this entire thing is for those who understand there's going to be like the confusion matrix for the classification. So we only have one label, so yeah, fully classified. The F1 curve, and then we also have the loss curve. So I'm going to show it over here. I think the results being, yeah. So the loss curve that I've shown you guys before in the PowerPoint. And then this is the train batch. Let me see if I can zoom it. Yeah. So these are the train. We also have the validation. So these are the validation. So as you guys can see, everything is fully classified, and our model is running great with the validation. So remember that the validation data is something that so it's not going to be like seen before during the training, but it's going to be validated after that. So yeah, so as you can see, everything is validated properly. So once we have this, so that's the first step. We're going to download the best PT. So how do we download it to our computer? Well, we can just press this download button here, right click, download, and then just put it somewhere that you want. So let's say for our case, we're going to put it inside, where is it? YOLO workspace, source, workshop, robot detection, source, robot tree detection, and robot model. So over here, I already done that. The best PT is already here, and the last PT is also already here. So don't have to do that. But if you guys want to do it, you can press the download button over here. So I've done it for you guys. So this should be like around 14 megabytes. Yeah. So that's the training step. Okay, let's go back to the presentation. Sure why the present button is not here. Okay, continue on. So we have trained. So that's how the pipeline works. So we have collected our data set, annotate them, train, and then, oh, we haven't tested them. So we're going to test them after this. But from the validation, you guys can see that everything is running smoothly. So yeah, we're going to test our model now. So what we can do is that once we download it, we can go to our container, our Docker container back, or to your device back. Then we can go, let me see. It should be inside the Turtlebot tree detection, source, YOLO v5. And then we can just go to this directory over here. Yeah, we can go to this YOLO v5 directory. Yeah, YOLO v5 directory here is already, I've already git cloned it and put it inside the repository that you clone. So you guys don't have to do that again. So we can go to this directory. So one of the script that you guys can try is that Python model inference.py. Let me see. Oh, Python 3. Model inference.py. And it's going to download the necessary thing at first, but after that, it's not going to do that. It's going to be saved in a PyCache. So right now, we already have done that. And you guys can see some number over here. So this number is the inference time. So I'm using a GPU, like a graphics card on my computer, on my laptop. So this is not inside the server. This is in my laptop. There's so there's a GPU. So that's why it's quite fast. Like the inference time is 16 millisecond. Millisecond. Yeah. And then over here, there's a list of lists. So since there are only one object, there is only one object in the image. Oh, I'm going to show you what the image is. So this is test image. So this is completely a new image that has not been seen from our data. So it's not inside the train and validation directory. So inside the model inference.py that I've created, if we run this script, we can see that there's X, Y, and then the confidence, which is 0.6, 60% confidence that it is a robot. So that is the output of this model inference.py that we're going to use later on. So the output, if you guys are wondering, is this one. So that's the test JPEG, and that's the output JPEG. So after training the model, we can already see the output. However, this is an image and not something that we can directly deploy on ROS, right? So we're going to see how we're going to use this and deploy it on our ROS node itself. So let's go back to the slides. So yeah, so we have done train, test, collection, and everything. So now we can integrate it with our ROS, yeah, our ROS tag. So inside here, what we need to consider is that I put it inside the source turtlebot 3 detection, and then that's the robot model that we have downloaded just now. And then inside the YOLO v5, we also have the model inference.py. So I'm going to explain this to you guys after this. So this is the one that we just ran over here, which is what we painted just now. So I'm going to explain this in a bit, as well as how are we going to integrate it with ROS. So let's go. So for ROS itself, we're going to use, there's a built-in type for image, as you guys can probably see here, is sensor message image. That is the one that we use to subscribe and collect data from. So remember the one that we use, not to JPEG. That one we actually use this, but you can see there are a lot of stuff that is like encoding, height, weight, and everything. So ROS actually provide a tool that can convert from OpenCV image, which is in NumPy array, to ROS message, which is this one. So you can see here, this is called bridge. So this is called CV bridge. As the name suggests, it's bridging between ROS message and OpenCV message. And here on the bottom side, this is the implementation in Python that you guys are going to actually use during your hands-on session that I'm going to explain after this. So first things first, what we need to do is that we need to convert the message from our subscriber, convert it to an OpenCV image. So to do that, we can just use image message to CV2, and then the desired encoding is just passed through. And then when we want to convert it back to message, we can say the encoding is BGR8. So BGR8 is similar to RGB, but the order is reversed. It's going to be blue, green, red. 8 means there's going to be 8-bit. So from 0 to 255, which is the common value, maximum and minimum value for image. So that's how we are going to convert this. And then the bounding box output, as you guys can see here, this is the X0, Y0 location, X1, Y1 location. And then the robot, the label itself, which in this case is robot. And the confidence is 0.61, which is the one that we got from thing here, the terminal over here. Yeah. Let me see. Yeah, it's 0.6065. Yeah. So 0.6065, which is going to be around to 0.61. So this is basically the same image. And then the output is a list of lists. So the first list is going to be a set of object bounding box. So if you have one image with multiple bounding box, there will be more. But for our case, there's going to be only one. So we can just disregard the entire nested list and just consider there's only like one specific list that we are going to use, which is this one. So X0, Y0, X1, Y1, confident and label. So for the bounding box, what we need to consider is the 4 coordinates, because the rest, I think it's not really necessary for our calculation that we're going to do with our pursue robot. So for now, we're going to do the X0, Y0, X1, Y1. So how are we going to, let's say, use this for our controller later on? Well, first things first, we need to actually show that we can do the inference on the gazebo itself. So over here inside the turtle bot detection, there's a node. So we have discussed about the node to JPEG just now, and the other one is inference. So inside the inference, there will be two functions that is given for you guys, which is load model and inference. And these are something that you guys need to do for the hands-on exercise that we're going to do in a short while, 5 minutes later on. Yeah. So in 5 minutes, you guys will be doing this. Actually, we might be doing it like in soon. So yeah. So first things first, what you guys need to know is that I've already created this template for you guys, and there's the load model and inference. So the thing that I've discussed is how to convert from sensor message image to OpenCV NumPy image that is using CV bridge, and similarly we convert from the image back to sensor message image using the CV bridge as well. That is already given here. And I already done the model, loading the model itself. So you guys don't need to consider like how are we going to load the model. It's already given for you guys here. And lastly, the thing that you guys need to do is to basically is for you guys to practice on how to convert from OpenCV from ROS message image that is subscribed from this topic, input topic here. So every time it receives a new image, it's going to call this function called the def inference pipeline callback. And how do you guys publish it? And in such a way, it creates a queue, like it's getting new image at the bounding box, create a new image and publish it. So that's the thing that you guys will be doing. So before we do that, some of you guys might be wondering how are we going to, I mean, I give you guys this load model and inference, but let's say you guys want to modify it for your own purpose or something, like add some additional stuff. So this model inference is completely created by not from the YOLO v5, so you guys cannot find it inside the, where is it? Here. So it's not here. So I've just created this for this specific workshop. So as you guys can see, the load model is basically loading the torch model and change it into the desired output that we want from our weight path. And then the thing that you guys might be wondering is the inference. So to do the inference itself, we need to convert the image, resize it to 640, as the model is using 640. And then we need to create it and normalize it to 0 to 1. Make sure that the image has the length of 3. And then we do the prediction. So after we have done with the prediction, we need to apply non-maximum suppression that is given already from here. So it's already given from PyTorch itself. So we don't need to worry about that. Lastly, we need to annotate. So this is where we draw the actual bounding box. So you guys can actually modify this. So later on, let's say you guys have your own application, you want to add something after the image has been drawn, like maybe you don't want to draw the bounding box or something, then you can just delete this annotator, then leave it blank or something like that. If let's say you guys want to add something else, let's say like for this one, I'm just going to add like normalize the pixel, the coordinates of the bounding box into 0 to 1 instead of using the pixel. But let's say you guys want to use the actual coordinate and don't want to normalize it from 0 to 1, then you guys can delete this, everything here. You can just modify. So you guys can modify whatever you guys like. So I'm going to give this to you guys, and you guys can do whatever you guys want. So that's why you can see over here, it's not giving the coordinate as in like some pixel coordinate, rather it's going to give you 0 to 1 because I modify this in such a way that it fits 0 to 1 for later purpose for the second exercise. So yeah, now we are going to do the hands-on exercise. As mentioned, what you guys need to do is to do this inference and ensure that these are properly filled. And I'm going to discuss with you guys on how to do this after you guys have done so. So I think at this point, you guys probably have like git clone and do Docker stuff and everything. And you guys might have some questions that you want to ask or something. So yeah, I'm going to break this to a breakout room right now. Maybe 2 breakout room. Yeah, 2 or 3 breakout room. Yeah. Yeah. So if you guys have, let me see. Yeah. So if you guys have any questions, you guys can just ask or share your screen if you have some problems that you are facing. As mentioned, we need to fill this inference pipeline callback. It's inside the template detection nodes inference. If I don't, okay. Yeah. Okay. So right now, I think we can go through it together because I'm not sure whether you guys have tried to attempt this or not. So we're given this function. We're given this function called the inference pipeline callback that is going to be attached to a subscriber that receives this based on the input topic that is given over here. So what we can do is that it's going to receive an image that is going to be sensor message image type. So first thing first, we need to convert it from sensor message to OpenCV. So I've given this inside the slides. It should be dot image to image message, yeah, message, and then we just need to say that the desired encoding should be passed through. Okay, so that's the first step. Done. Then the second step is to use the function inference and get the bounding box, and then set the maximum detection to 1. Okay. So first things first, what we're going to publish is a float 32 multi-array of a B-box topic that is already specified. So we don't need to know what is this topic, but we need to know that we're going to use float 32 multi-array. So we're going to define some array that is float 32 multi-array. And then we're going to put the bounding box inside the array if only the data is available. So if the bounding box is not available, we're not going to get it. So first thing first, we need to get the bounding box. So the bounding box is going to be taken from this inference function that actually, let me see, this inference function is taken from this model inference. That's going to take in the model and the original image. It also have additional stuff like the maximum number of detection. So we can actually set that here. So what we can do is that we can set this. So the first argument is going to be the model. So that's the first argument. The second argument is going to be the image. That is the OpenCV image. And then we can specify the maximum detection to 1. Yep. And then the bounding box array here, we're going to use it for step 3, I think. Yeah. So the step 3 is to, if there's an object, we need to take the first 4 element and put it on a float 32 multi-array. So we put this bbox array over here. And then what we need to do is we need to check if the bounding box consists of element of, or it is just nothing. And then we're going to put it on the data, bbox data, array data, bounding box is 0, 4. Yeah, so if you guys need help with the like auto completion, you can just press install in the container, install pylon, and I think that should help with doing this. Yeah, because some of the syntax should be highlighted, but it's not highlighted yet. So yeah, we might need to install it here. Okay, now the syntax highlighting is better. So yeah, okay. So lastly, we need to specify, once we get the data, I think that should be all for step 3. And then the last step is that we need to publish the bounding box, right? So to publish the bounding box, first things first, we need to publish the bounding box. So we have the bbox publisher, we have the publish the bbox array. Then second thing is that we need to publish the image. So the image, we have to convert it back to OpenCV, from OpenCV image to ROS message. So we can do it by doing this, I think bridge. Then we need to convert from, let me see, CV2 to image message. Yeah. Invert image. Then the encoding should be BGR. Yeah, you can see here the encoding thing. Yeah, the BGR 8. And then we publish this inference publish image message. So now we're going to test this, whether this code works or not. So we go back to this launch file. I think for now, we're not going to collect more data. So we can just disable this one, we disable. So we're not going to collect data. This one we're going to enable. So let me see. Okay. So we're going to uncomment this one. So yeah, we're going to enable this TurtleBot detection launch that is going to run this inference node. So yeah, everything is running properly. Now what we can do is that we can launch it. So let me go back here. Make sure everything is okay. I think cat can make or cat can do, just to be safe. We can close this one. Okay. So now we can do ROS launch, TurtleBot 3 bring up, and then TurtleBot 3 pursue. So this is not going to pursue yet because we haven't done our controller logic and everything, but we need to see whether we're getting the inference. So yeah, as you can see, we're getting the inference that we just created just now. So that is what to be expected. Yeah. Okay. Okay. So now that we have got this inference right, and we already got the bounding box array. So let me show you the bounding box array. We need to create another terminal inside the container. So let me clear this first. So ROS topic list, and we can see a lot of topic being listed here. We can see there are the TurtleBot 1, TurtleBot 2, and we just created this image inference that we have seen from Arvis. We can also subscribe to this bbox array. So let me subscribe to this. Let me clear first. First topic echo. And as you can see, we're getting 4 elements, which are the X, Y, x, y. So those are the two coordinates that we need to determine the bounding box. So up to this point, I think you guys have understand how to subscribe to an image, do something with it, like let's say do some inference or create a bounding box array using float32. Yeah. So now the next step is to actually deploy it with a controller. So as you guys can see, the robot is not pursuing yet because we haven't create a controller to pursue this robot. So how are we going to create this? Well, from the previous workshop, we actually already have this template that is given inside the TurtleBot3 controller. So yeah, this is actually from the previous workshop, and I modified a bit. And the next thing to do is that what are we going to do with this controller? So we already have a PID controller that is programmed over here, and I already tuned it for you guys that is located here. So what you guys need to do is basically, where is it? Yeah. So what you guys need to do is basically add this file, add this script over here to actually from the bbox array that we just subscribed, we want to get the x mid location, y mid location, and everything. So I'm going to explain this part for you guys. So we have done this, and the next part is that we're going to do pursuing. So how are we going to pursue the robot? Well, the simple way to do it is that if we detect the robot in our screen, then we want to go to that specific angle that is given. And this problem, we have done it previously. Instead of doing it with the robot, we're doing it with a pillar. So I presume you guys have done this previous workshop and successfully hit the pillar with your robot. So that's basically the same idea. However, this time the robot can move again, but the PID controller should be able to handle moving robots as well. So what are we going to do? First, we need to understand that OpenCV image actually starts from top left instead of from bottom left. So the Y is actually going from top to bottom, 0 to the image size. However, I've normalized it as I mentioned earlier. So it's going to be 0, 0, and 1, 1 over here. And then in between, it's going to be like in the middle here is 0 0.5, 0 0.5, 1, 0 0.5, 1. So what we need to do is that we need to detect where is the location of the robot in our image with respect to our center. Because technically the camera is located on the center, so we need to know how are we going to steer the robot based on the image itself and the bounding box that we have, the bounding box array that we already got. So as you can see from this diagram here, we need to get the x mid and y mid from 0 to 1. And since we have normalized it, it's going to be fine. So how are we going to get the x mid? Well, technically the x mid is just the middle of this, right? So it's going to be x0 plus x1 divided by 2. And the y mid is going to be the same. So it's y0 plus y1 divided by 2. So that is how we're going to get this location from the top left. However, we want to get it from this middle, right? Bottom left, bottom middle, as this is what our robot is looking from. So how are we going to convert from looking at from here to here? Well, the simple way is that if we have the y mid coming from top to bottom, we can just use 1 minus of it, and that will be from bottom to top. So bottom to here, that should be 1 minus y mid. And then for the x-axis, since we're going to see it from the middle, then we are going to do 0.5 minus of the x mid. And remember that the geometry twist is following the right-hand rule. So for this case, the z-axis is going to go, if we're using the ROS coordinate, not the OpenCV, the z-axis is going to be, the z rotation is going to be counterclockwise, not clockwise. So this is the ROS convention, and since we're going counterclockwise, we need to make sure that going to the left means we're getting positive value, which is why we have the 0.5 minus x mid and not x mid minus 0.5. So that is what we need to program. So we need to get this and this into our controller. And yeah, we're going to do it now. So for the hands-on exercise, we have done it the first time. And for the second one, I'm not sure whether we're going to do a breakout room again, because I'm not sure, because yeah. So I think we're just going to discuss over here right now. Yeah. Okay. So if you guys have any questions or doubt, you can ask with regards to this, or if you guys want me to code it directly, I can also do it for you guys. If you want to ask regarding to YOLO or ROS in general, you guys can also ask. Yeah. And in 5 minutes, I'm going to discuss this. All right. I think we can discuss it right now if you guys have no issue with that. So first thing first, we are given this X meet and Y meet that we need to compute. And we already know the formula from here. So what we need to do is that we need to get this done first. So step one, check if the robot is detected. Basically, we check whether the data size is 0 or not. If the data size is not 0, then there's something to be detected. Okay. Then the second step is that if it is detected, then we need to get the pixel location of the middle of the bounding box. That is the one that we just discussed. And that one, we can get it by doing this. So we need the message. Okay. Let me see whether the C++ to completion works. Okay. Container. Yeah, let's install C++ as well. Okay. Oh, not sure whether it helps. Okay. And then, so that's the first element. And then we need to add the second, not the second, the third element. So that's going to be the x0 and x1. Then we divide it by 2. Since we already defined it to be float, then that should be fine. Don't forget the semicolon. Similarly, for the y mid, we do the same thing. So I'm just going to copy this in nothing. Yeah, copy this, change it to y, add 1. So 3, 3, done. And then this is with respect from the top left. So if we want it to be from the bottom left, we can just use the 1 minus of that. So this is going to be from bottom left. So if you want it from top left, just leave it like this. Then step 3 is to get the angle from the center of the robot to the target in degree. So to get the target angle in degree, first we need to get the target angle itself. So what we need to do is that we need to get the target angle. So I'm going to define it here. And then we have a tan2. That's a math function that is given. So a tan2, we just need to provide the x and y. So for this case, if you see here, the angle is here. So we want this to be the y, or although it's x, we want this to be the y of the argument. We want this to be the x. So 0.5 minus x mid and 1 minus y mid. So that's what we're going to compute. So we just need to put 0.5 minus x mid for this. That is the one that is given. So for there, then this one, we want it to be 1 minus y mid. Yeah. So if you've done like 1 over here, then you don't need to do the 1 here. Okay. So this is already okay, but we want it to be in degree. And I think a tan2 returns it in radian. So we need to do some processing, which is multiplied by 180 divided by pi and pi. Yeah, 3.1415. Okay. So now we have converted from radian to degree. So that's the first thing. The second thing is that we need to get the area. So the area is for us to actually gauge whether the robot is quite close or not. Because if the robot is close, then the area should be big, and we don't want it to be quite fast because maybe the target robot change its direction if we're quite close to it, and then the robot won't be able to like stop abruptly and then change its direction. So this one we might need to set it. And if the robot is far away, the area will be small, and we want it to be fast. So that's the idea behind this. So we need to set it here. So the area should be the difference in y and the difference in x, and then we just multiply. And the reason why we don't need to, let's say, take care of the symbol, like let's say bottom minus the top one, is because if both of them are negative, that's going to cancel out each other. So let's say we get the negative delta y here, negative value. This one is also